Hi, everyone. Yeah. Anyone get the right answer to the last one, for the last one? Is that the one about the capacitor and something charges up and turns on and turns off and turns on and turns off?
The neon tube.
It doesn't tell you the formula you're trying to derive. It says kind of show that this is the delta T, or maybe they call it capital T.
Part A, that was part A.
Okay. And verify and show the algebra to derive this equation, and part B was gave you some numbers.
Yeah, you had to find the resistor with the value of the resistor.
Ah. Yeah. Well, I think we will maybe spend some time. Well, we could talk about either of those homework questions a little bit. There will be circuits on the test. It's kind of why I put some of that in the homework, because we haven't seen that as much for a while. Let's get it down. So basically, the plan for today is going to kind of go through this question and kind of consider these two segments of roof. I briefly showed this on Wednesday. I was hoping to get a little further on it on Wednesday, so I'm going to do that now. Again, this is an analogy for magnetic flux. Magnetic flux is part of chapter 33, along with induction and Faraday's law. That will not be on Monday's test. So we're going to go through this and then switch over, hand out some practice test questions, or kind of point you to several practice test questions and solutions, and talk about maybe what to expect and for the test on Monday. So I think we're going to do the test as we did the previous one, with half of you guys up in this room and half downstairs. I believe the capacity for this room is considered a little bit higher than downstairs, so I think maybe we'll have group B up in here and the 9 or 10 people from group A in the lab room.
So basically the same way that the previous test was?
Yeah, I think that was on a Wednesday, but I think we'll do it the same way. We'll aim to do it the same way today, 1 or 2 people in a different spot. It's not a big deal. Doesn't really matter to me too much which room somebody's in. Okay, so let me kind of put this up here, and let me kind of motivate this briefly with a definition that this question here is about sunlight. It's not about magnetic field, but just wanted to kind of give an analogy, an analogous concept. So what is the definition of magnetic flux? Which is the concept that is very central to many of the calculations, not quite all, but many of the calculations in chapter 33. Capital phi, sometimes phi m, to make it clear we mean magnetic flux, because you can do similar calculations with electric field or even gravitational field, but in particular you'll see references to phi e in the Gauss's law chapter that we skipped over a little bit, 27. So let's say phi m. I'll give the most general definition here, which involves an integral. And then I'll give the one we're going to use, definition of magnetic flux through a surface. So it's an integral of B times area. It's basically magnetic field times area is the core concept there. Directions matter, which is very much what this scenario is kind of trying to get us to realize or think about in an intuitive way, hopefully. And the idea would be here, it'd be something like there'd be some kind of surface, and we'd want to know what's the magnetic flux through the surface. So we'd kind of define, like, let's say into the page to be the positive direction, maybe out of the page negative. So like there's magnetic flux a certain direction. Basically the question is kind of like, how many magnetic field lines kind of pierce through this surface going that way, or pierce through it going the other way? that would be kind of visually kind of basically a way to measure flux. It's like you pick an area and you kind of count how many field lines pierce through it. If you increase the strength of the magnetic field, what happened to the field lines? They're closer together visually, so more of them would kind of insert into a certain region. If you increase the area, you're going to catch maybe more field lines. Of course, if you increase the area enough, you might start to have some field lines go through in one direction and then cycle back around and come back the other way. So actually having a bigger area doesn't necessarily mean more net flux in a certain direction. And then the directions matter. So it's like if the field lines are piercing straight in like this, you'll get more flux than if the field lines are kind of coming at an angle. But you could have something like here, the magnetic field is represented by dots kind of coming out of the page and they're close together. So this is kind of like high B. And then you could have dots, but maybe they get kind of more spaced out. And this is kind of like weak or low B. So you can't kind of say what is the magnetic field for the entire surface. But we're going to do a lot of situations where if B is a uniform field, so B is the same magnitude and direction everywhere, same vector, magnitude and direction everywhere, same vector everywhere of interest at least, then what's going to happen to the magnetic flux? Then the magnetic flux through the surface, you don't really need to do the integral, you can just kind of multiply. So this means like consider every little patch of area. So what is dA? dA would be like this little box. And then the next dA would be this box. And the next dA would be this box and this box and this box. And if we add up the flux through every little box, we get the total flux through the loop. But what if every box encloses the same strength and direction of magnetic field? Then you can just kind of do B dot A. Now the directions are still going to matter here. And a couple ways to think about this is how do you do a dot product? If you have unit vector notation, you could do unit vectors. But in general, a dot product is magnitude of the first vector, magnitude of the second vector, and then we want to know how parallel they are. And that is usually represented by cosine of some key angle. And the cosine of the angle would be the angle formed by, and this is where I'm going to try to draw a 3D picture. Maybe I'll do A is like purple. So it'd be kind of like, let's say this is your surface and it's supposed to look like it's kind of angled a little bit into and out of the page, kind of like lying in this kind of plane a little bit. So let's say this is your area, then your area vector would kind of point perpendicular to this surface. This is the area vector. And then the magnetic field vector might be, there's magnetic field kind of pointing through this way. So the magnetic field vector points in whatever direction is parallel to B. And then what's the angle we're talking about? We want to know what this angle is right here. Cosine theta. So keep in mind, similar to the magnetic moment vector, the area vector is perpendicular. By definition, it's perpendicular to the flat orientation of the loop. So the wording can get a little funky. Like if you use words parallel and perpendicular, it can get a little funky because what kind of scenario gives us a lot of flux? Here's one thing you could say. You get a lot of flux when the magnetic field is parallel or nearly parallel to the area vector. But that actually means you get a lot of flux when the magnetic field is nearly perpendicular to the loop itself because the area vector is perpendicular to the orientation of the loop. So maybe just at some point kind of think about that. So in this case, I'm kind of in the middle here. I know I've got an angle probably close to about 45 degrees or so there. Where's the textbook? That's a better example. And now we'll flip the other camera here for a second. You know, so keep in mind, it's kind of like this. It's like as I move the book around, the area vector points out of it. So parallel to the vector means perpendicular to the loop and kind of vice versa. Now let's do this guy here. Here we don't have a magnetic field, but I kind of tried to use the same color. We have something with a direction and kind of a strength to it, and that's represented by the sunlight here. I'm going to give you a number for the sunlight. It's going to be very different units than magnetic field units. Something you look up, if you look up a number called the solar constant, it's kind of the average intensity of sunlight when it reaches Earth. And usually that's around 1300 in some units. I'm going to go for a number around there. And I'm just going to say the sunlight kind of has a brightness of 1300 watts per meter squared. This would often be called intensity. Maybe I'll call it I. But this is our analogy for the magnetic field. It's got a direction, it's got a strength to it, but it's kind of the same uniform strength and direction everywhere of interest. And then what was this supposed to represent? This is like we're looking at the end of a long building. The building points into the page, 100 meters into the page, and then the roof has these dimensions. It's 80 meters wide, but it's angled, and the peak is 20 meters above the corners. And what I'd like to do is I'd like to calculate what is the power being absorbed by this panel, by this surface, and what is the power being absorbed or incident, you might say, on this surface. You could reflect it or you could absorb it. So I'll just say, how much power is the sunlight delivering to the, let's call this like, I'm gonna call this kind of south and this north, because that's probably what this would be. Actually, in the northern hemisphere is the sun's kind of in the southern half of the sky in the middle of the day, especially in the winter, it's in the southern half of the sky all day. And so it kind of hits one surface more efficiently for delivering energy than the other one. So we're really focusing on here is this cosine theta piece, or the dot product of the cosine theta, because the strength or the intensity is the same at the two roof surfaces. The area of the two roof surfaces is the same. So what is the area of each roof panel? You can do your Pythagorean theorem here. So half of 20 is 40. So like 40 squared plus 20 squared square root. So I think I'll just kind of, I'll say the width of each of these is the square root of 20 squared plus 40 squared. Probably should have picked nicer numbers. And that's about 44.7 meters. The length is kind of written over here. I'm going to call length the into and out of the page direction because it's the longer of the two, but it doesn't really matter. That's 100 meters. So the area, is just 447 or 44. I'll give another digit here. 44.72 meters. So 4,472 square meters. And of course, that's kind of true in either case. So maybe you could either call that maybe we'll call this 1 and this 2, but the areas are the same. The intensities, which is like the magnetic field, is the same. But it would be totally inaccurate to just multiply these two guys and say, oh, so the power on both roof surfaces is 1200 times 4472 watts. What's that missing? It's missing this directional stuff. So what we need to do is you need to ask yourself, basically you need to do a dot product. And you need to do a dot product, or basically you need to ask yourself, okay, that's the area, but what is the area of this roof panel perpendicular to the incoming sunlight direction? So, like maybe go back to the other camera here. That's this. Okay. That's the surface area of the book. But if I hold the book like this, it presents less apparent area from a certain perspective. Also, things like, kind of like walking through a doorway, like you can hit it straight on and then you get the full area. But if you kind of come at an angle, it's like you really have kind of less area to deal with. And what we really want to know there is, in some sense, what we'd really like to know is what's the area of this? I'm going to talk about this roof panel here. We'd like to know, that one's almost perpendicular. I might not try to draw it because we kind of want to know like perpendicular to the incoming sunlight, what's the area? And that's not quite going to be the same as the actual area of the roof unless you're hitting it dead on. And it's going to be quite different for the two sides here. So over here, it's going to be much less. So where's this angle that we should take the cosine of? We need to take the angle between the area vector and the magnetic field or the intensity. So I'm going to draw, now here I could kind of arbitrarily either draw the area vectors pointing that way perpendicular to the loop or that way. I think we know what the direction of the flux is in this case. It's downward at the roof. So I think just to kind of be more clear, I'll kind of say here's a vector perpendicular to this one. That's maybe the A1 vector. And then here's like my I vector, which is kind of like magnetic field. Over here, here's my I vector. But now my A2 vector is perpendicular to purple. A2. I could label them I1 and I2, but they're the same. So in this case, I need to take the cosine of that angle, and in this case, I need to take the cosine of this angle. So we just need to do a little bit of trig and figure out some angles, basically. So if you were told that the sunlight's coming in 45 degrees above the horizontal, see that there? And then you were told the 20 and the 80, could you work out these angles? And I think we'll just do that kind of work down here. 20, 40, there's that. And then this is perpendicular. So let's try to find kind of an angle in there. Maybe if we could eventually figure out how many degrees is this from horizontal, I think that'd be nice because we know the sunlight's 45 from horizontal. So just like what's an angle in here? So let's see, let's find this angle right there. That's the inverse tangent of 20 over 40. Maybe we'll call that alpha is the inverse tangent of 20 meters over 40 meters. And inverse tangent of 20 over 40, make sure I'm in degrees, is 26.6 degrees. And I think that means like this is 26.6 degrees also, kind of from the horizontal. And then this is perpendicular. So if that's 26.6, this is 90, and this is going to add up to be 180, or basically these two angles together make 90. So 90 minus 26.6. And I think right here, we get 63.4. So the area vector, or the A1 vector, is kind of like 63.4 degrees from horizontal. Whereas the incoming sunlight is at 45 degrees from horizontal. So the angle I need to take to consider in the dot product is this angle take away 45. They're not parallel. They're not too far off though. They're out of alignment by 45 degrees less than this. So I'd say theta 1, you know, because this is like 45 degrees right here. This is 45 degrees. And I want to know theta 1, which is the difference here. So theta 1 is 63.4 degrees minus 45 degrees. And that's like 18 or so. 18.4 degrees. And maybe while we're at it, before we do this, so basically let's do we're going to do 1200 times 4472 times cosine of 18.4. I'm just going to maybe list what is the cosine of that angle. That's a dimensionless number. What's the cosine of that angle? 0.949. 0.949. So like the alignment here is kind of like 94.9% efficient, kind of. We're going to get 94.9% of what we could have gotten if we could have oriented the roof to whatever angle we wanted to pick up the most incoming sunlight. And of course, the sunlight's going to move throughout the time of day, and this is kind of maybe at one moment. What about theta 2? theta 2 is, here's the other side of the roof. And we know that the angle is 63.4 degrees below a horizontal. So theta 2, sorry, A2 is right here. And this is 63.4 degrees below the horizontal. And then we got our other guy coming in here at like 45 degrees. And this is 45 degrees. Does that look right? I think I've got that kind of drawn pretty much correctly. That should have been red. So what's the angle in between there? I think I have that correct. Does that look correct, people? So theta 2 is whatever that comes out to be, maybe 180 minus 63.4 minus 45. I got 71.6. So theta 2 is 71.6, and the cosine of theta 2 is kind of like a dimensionless factor. And for that, I got 0.316. What do we get for the energy or the power? What's the difference between energy and power? Power is energy per unit second, per unit time per second. So what is the power hitting the right panel and the power hitting the left panel? Well, let's see, get another blank piece of paper. So power 1 is the intensity, 1200 watts per meter squared. That's kind of like B. And then the area, 4,472 meters squared times the cosine of 18.4. And power 2 is the same, the cosine of 71.6. And I think if you look at this, maybe it's because it's 45 degrees. It's probably because it's 45 degrees, but these ended up being kind of complementary angles. But I think that's due to the 45 in there. Wouldn't necessarily have to be the case if it had been a different sunlight angle. 1200 times 4472 times cosine 18.4. 71.6. 1, 2, 3, 4, 5, 6. I'll put this in 5.09 times 10 to the 6th watts. 1.69 times 10 to the 6th watts. If you wanted, you could call that megawatts. And this would be analogous to what we're going to call the flux. One is receiving a greater, this is like an energy flux, and what we're going to be talking about is magnetic field flux, but it's receiving a greater flux. Now we can't do this, but if you could move the roof panel around, I'm kind of thinking like, what if you're like you design solar panels, and you want to build solar panels to pick up a lot of energy. Of course, the sun moves throughout the course of the day, but at this particular moment, if you could move your panels, you'd want to move them to be perpendicular to this. You'd want to move them to be 45 degrees above the horizontal to be perfectly normal to the incoming direction. And then you would get, 1200 times 4472, whatever that number is, which is 5.37 instead of 5.09 megawatts. Friend of mine has worked in mechanical engineer. He's worked in solar power. He's worked for solar power companies for many, many years of different sizes and seen a lot of changes in that industry. And one company he worked for is called Ray Tracker. And they built panels that would, instead of being at a fixed position, they would kind of move throughout the course of the day. They'd point south, but they would move from being kind of vertical near sunrise and sunset and kind of tip back and slowly change orientation, trying to stay perpendicular to the incoming sunlight throughout the course of the day. And there were some challenges with that, but you can see how overall maybe it takes a little bit of energy to do that, but you absorb more energy over the course of the day than if you just kind of sit at one angle that's kind of considered optimal for that latitude. Okay, so you're kind of, this is what we mean about flux. So we might do a problem, we could do a problem like, you know, if you rotate a coil from one position to another position, that's going to give you a changing flux because the cosine theta piece is going to be changing. And as you have a changing flux, you can induce current in the way that we did some examples of on Wednesday, worked out some Lenz's law examples of on Wednesday, and also saw demonstrations of a week ago in lab. So something to think about. And this is pretty relevant, you know, if you kind of look at a building like this, if this is south and this is north, maybe if the building's aligned pretty well along kind of an east-west line, you're going to see kind of a different amount of probably snow melt in the middle of winter, maybe after a couple sunny days in the middle of winter on two surfaces of the roof, because there's a difference here. So that is maybe something to keep in mind when kind of thinking about this guy here. We want to get close to perpendicular, but in perpendicular will mean that these two vectors are close to 0 degrees in difference of angle, and we take a cosine. There could be a bit of a sign here. I could imagine somebody distinguishing between positive flux, zero flux, and negative flux, but what's positive flux versus negative flux mean for a surface? Basically, just like which way is the incoming magnetic field piercing it? Are you piercing it kind of in the front cover of the book out the back, or are you piercing it in the back cover out the front? Of course, if you were to have a book, I think we had a situation like this on Wednesday, like if your magnetic field were going this way, if you flip the coil from here to here, that's a very large change in flux because you went from like 700 units of flux into the front cover and it became 700 units of flux out of the front cover. You kind of, that's a sign change. So there is a sign here. The signs get a little funky, and that's why we often fall back and rely on Lenz's law to help us get the direction of the effect correct, so we don't have to concern ourselves at every step of the way as closely. We don't have to concern ourselves every step of the way with what's the sign of this step? What's the answer of this step? What's the sign of this step? It's like, we'll do a calculation to get the magnitude, not worrying about directions a whole lot. And then separate of that, we could think through Lenz's law and say, okay, the flux is outward and increasing. Lenz's law says that you're going to oppose that. So if you oppose an outward increasing flux, that's a decreasing flux. That would be like, let's create some inward flux and then do right-hand rule to find an orientation that goes with that. There's nothing down. Okay, so that's what I was hoping to get through Wednesday and today, although this is not on the test. What will be on the test is calculating magnetic field from different current arrangements or finding forces or torques on certain currents or charged particles due to the presence of a magnetic field. Those issues are irrelevant to the test. So at this point, let's see, I'm going to ask what questions people are kind of wondering about maybe this demo here, about the roofs. Or we could look at the homework a little bit. I know there's only the 2 questions. So what were the 2 question numbers? 65 and 80. Oh, way too far. Way too far. 65, yeah, right. I would say 65, what do I mean by 65? Circuits like 65, maybe with a couple branches, more than one battery in them, is definitely something that there will be something like that on the test. I don't know if the question will be worded the way this question's worded, where we don't know one of the battery voltages, and here they're using this symbol EMF for battery voltage, essentially. It's measured in volts. Here we don't know the battery voltage, but we have a circuit of this kind of shape or style is definitely something that is gonna probably be on the test. There's an example question on the practice questions I'm about to point out that has a fair amount in common with this. There's like I think there's 3 branches and 2 batteries in the question. I'm thinking of this one has 3 branches and 2 batteries. For what EMF does the 200 ohm resistor dissipate no power? Should the EMF be oriented with its positive terminal at the top or the bottom? So they didn't even want to draw the battery in there and kind of make you think one way or the other. They want you to decide that. Anyone want to say how you thought that one through, how you would kind of apply our concepts to start to write down something kind of numerically capturing the concepts of this circuit here? No power. No power in a resistor. What would no power in a resistor mean?
No current flowing through it.
There's no current flowing through it. So in general, there'd be 3 currents in this circuit, right? In general, there'd be like a left current, a middle current, and a right current. And in general, every resistor would probably have a different current amount. And what they've gone to is they've dialed things around. It's like we're dialing the voltage up and down on the right battery, and we're kind of observing the current on the middle branch until we get to 0. And we did a lab where we dialed the voltage up, and we went from a negative current as detected in a certain portion of the circuit to a positive current by the end of the run. And we kind of asked ourselves, at what point did we transition? This is basically about that transition point.
It was double the voltage.
And in that case, there was a 3-volt battery, a 5-volt battery that was fixed
There was a 5 volt
amount.
at the bottom though.
Yeah.
And then you got your variable voltage in the middle,
Yeah,
and you had to crank that middle one up to 10.
yeah, and that probably had something to do with the resistances that were used on the different branches of that
It
circuit.
was 900, 720, and 360.
Yeah, and if you have 0 current in the top branch, then the 900 value becomes fairly unimportant because it gets multiplied by 0 current to give you 0 volts and 0 power. But the important ones were the 360 in series with the
360,
5-volt battery.
720.
And basically because 720 is double 360, the one voltage would have to be double the other one. So double 5 and get 10. So we're seeing something like that here. What's the voltage ratio here?
I think the answer is 150 volts for 30 minutes. So it's
Yeah.
about 3 times
Yeah. In this case, and then which way should we orient it?
the same direction as the other batteries.
Yeah, we want them to have opposing, what do you mean by the same direction?
The positive on the bottom.
Okay, that's what you mean by the same direction?
Yeah.
Because I probably would have said that the other way around, but that's
So it's
the right
direction.
direction, yeah. So what's the current actually gonna do? There's gonna be no current on the middle branch, but there probably will be current somewhere. What's the current kind of doing? It's just zipping around the outside. And basically, if you did I1 for the left branch and I3 for the right branch, I1 would equal I3 at this particular setting because they differ by I2, and I2 is going to be 0. What's the voltage from top to bottom here? There's 0 volts. So maybe another way to say it is you can almost do a voltage kind of volt loop right there. Actually, that would just, you could do that over there and get the current. What current will flow around the outer edge of this? I think it's going to be half an amp. There's going to be half an amp, and it's going to work out that all the voltage we gain on this battery, we drop across this resistor. So from the bottom middle node, we rise 50 volts, and then we go through half an amp at 100 ohms, and we drop 50 volts. So what's the voltage from bottom to top? 0. And then what do we do from here to here? We continue on, and we drop another 300 ohms times half an amp. So we drop down 150 volts. So this corner would be like negative 150 volts relative to the bottom. And then we rise through a 150 volt battery, negative terminal at this end, positive terminal at that end. And we arrive back at 0, and it all works. And I think that's pretty good example there. You know, if you wanted to, I would say you could just kind of write out Kirchhoff's rules, and at some point you're going to plug in I2 equals 0. And you could either do that in a more intuitive way and say, oh, this is what will happen if there's no current here. Or you could just say, these 3 equations describe the circuit at all operating values. and I just want to now say, I don't know this voltage, instead I know a current. And kind of it's a little bit of a one-for-one game. What would the most standard problem be? I think the standard problem would be, I know all the resistances and I know all the battery voltages. I'm told all the elements values. I'm told the key value for every element. And then what do we ask for? Find a current in the 300 ohm resistor, 200 ohm resistor, something like that. Well, if they want to withhold a piece of information and not tell me the battery voltage on the right battery, then they better give me some piece of information about a current somewhere, or maybe they could say the voltage across the 300 ohm resistor is 72 volts or something like that. And then they could have said, what is the battery voltage EMF? And is it oriented this way or that way? So, yeah. And if you connect a wire between 2 points at the same voltage, it's the same as if you didn't connect that wire. If you connect a resistor between 2 points that are at the same voltage, and you take that wire away, it has no effect on the behavior of the circuit. And you might kind of keep that in mind a little bit if you were to try the extra credit, the homework extra credit, the circuit resistor extra credit, I would say, with the cube in particular comes to mind. One of the scenarios for the cube, there is a wire that carries no current. In one of the different possible connection points, if you looked at, in one of them, if you do the analysis, if you kind of think it through based on symmetry, you'll come to the realization that, oh, this one wire here, or maybe more than one wire, but there's a wire here that doesn't carry current to the left or to the right, it carries no current. And you could interpret that very much like this wire carrying no current. There's a wire with a resistance, but the two ends of the wire are connected to the same voltage. Neither point's higher than the other, so current doesn't want to flow downhill in either direction, so it doesn't flow. Oh, this is obviously I'm just kind of seeing these side by side. They did a different question, but I'd say this is the more standard version. Why? Because we know both battery voltages. We know all three resistances. This is supposed to represent a dead battery, a good battery being jump started, but there's really kind of a third branch in the circuit, which is the starter mechanism is represented here very crudely as a resistor. And the resistances are really, really low, right? Resistances are really, really low in this circuit over here. The battery voltages are supposed to be 12-ish, but the dead batteries drifted below 12. Actually, the main reason, does it say that here? Yeah. I think I'm just going to read this because I think it's a little interesting. A 12-volt car battery dies, like this middle branch. Why is this a dead battery? And they're accentuating the voltage drop by calling it 8 volts, but what they're saying is the real reason a battery goes dead is the internal resistance kind of builds up as crud builds up in there. So having a greater internal resistance in series with this battery effectively blunts its outward effect on the rest of the circuit. How many volts is available to the rest of the world? A car battery dies not so much because its voltage drops, that happens, but because chemical reactions increase its internal resistance. So here we have a drop in voltage down to like 2/3 of what it's supposed to be. But what happened to the internal resistance? If this is a new good battery represented by 0.01 ohms, this cruddy one is 50 times the internal resistance, and that's probably going to have more of an effect on it seeming dead, it seeming very weak. And sometimes people talk about cranking volts or cranking amps, if you've heard that. So like if you just had this middle branch battery, if you just take this out of the circuit, you just have this battery. If you just put a voltmeter on this battery, what's the voltmeter going to read? It's going to read 8 volts. And let's say it was 11.5 volts, just a little bit below 12. It's going to read 11.5 volts when there's no current going through it. But when there's current going through it, a pretty good chunk of those 11.5 volts are going to be eaten up by this half-ohm resistor, because this half-ohm resistor came out of the box brand new as a 1/100th ohm resistor. And because it takes a bigger bite, the actual voltage available at the outlet terminals of the battery will probably be less than like the open circuit reading of 11.5 volts or the open circuit reading of 8 volts. Anyways, a good battery connected with jumper cables. Of course, positive to positive has been connected, right? Negative to negative. That's kind of how you do that. can both start the engine, get enough current through this guy to do what the starter needs to turn over and do his job, and recharge the dead battery, at least partially. Consider the automotive circuit. How much current could the good battery alone drive through the starter motor? How much current is the dead battery alone able to drive through the starter motor? With the jumper cables attached, how much current passes through the starter motor, which would be the sum of A and B? And with the jumper cables attached, how much current passes through the dead battery and in which direction? I think we're probably going to find it passes through the dead battery in the non-standard way for a battery, in the positive terminal, not the negative terminal. And on this one, they do a graph here. What does this graph look like if you don't have this weird mechanism that turns on and off? It's just an exponential increase that levels off to a plateau, which would be the battery value. And they're saying, oh, we are approaching, what is the battery value in part B? 90 volt battery. But once we get to 80 volts, something kind of eats up a bunch of voltage, and all of a sudden it drops, and it drops not to 0, but to 20, and it builds up to 80, drops. It's on its way to 90, hits 80, something flicks on for a second, flicks off very briefly, and we go on. There's some kind of time here. And it's basically an algebra exercise. It was more or less intended, I just want to say this, it was more or less intended that you could kind of take as a starting point maybe an equation of this form here. Did people kind of use something like this as a starting point, like a 1 minus e to the negative time over time constant? And this is charge, but if you wrote V and Vmax, that would be appropriate statement for the charging, the volts, the charging process of a capacitor. So it was intended, you didn't have to really like do all the derivation to get to here. It was like intended to kind of start with something like equation 13.36, the last equation of chapter, sorry, 31.36, the last equation of the chapter. And then basically, if you multiply both sides of this by capacitance, that turns charge into, you divide both sides by capacitance, that turns charge into voltage, and we could just write V and Vmax. And then you could kind of work it out. Mainly algebra. Kind of like there's a V off, maybe with a T off, and there's a V on with a T on, and we want to find the time difference, T off minus T on, something like that. Or maybe on minus off, I should say. But anyway, subtract them. Do some algebra. All right. Let me show you some practice questions and talk a little bit about test. So test on Monday. Again, if maybe have people from Group B up here in this room, 4th floor, Group A in front of me right now, downstairs in the lab on 2nd floor. And if you want to kind of start taking the test around 11 o'clock or so, that's fine. That's what quite a few people did a month or so ago, 4 weeks ago. So same. I think I will probably post on Moodle like an example equation sheet, but kind of let people do that on your own. I'd say the main topics that I'm trying to get to are, about half on circuits, maybe a little bit less than half on circuits, and a little bit more than half on magnetism, points wise, I'm thinking. Probably about 2 questions each. For circuits, questions about, or just understanding of, for circuits, understanding about series and parallel concepts, and understanding of Kirchhoff's laws, applying confidently Kirchhoff's loop rule to a circuit, confidently applying Kirchhoff's node rule to a circuit, and really the 2 of them together. And then on magnetism, there will definitely be at least one question or part of the question, which is about find the magnetic field at a certain location due to some source charges, source currents, sources of magnetic field. So B equals equations. And I think the main ones we had were we had magnetic field of a long straight wire, magnetic field inside a solenoid, and magnetic field along the axis of a circular current loop. And then at least one question or part of a question on okay, what is the effect of the magnetic field? What force does it apply to a charged particle? How will the charged particle's motion be affected due to the magnetic field? Or how will one leg of a loop or one wire or a loop react? So questions about like force and torque, where B is one of the inputs. And of course, all over this, we're talking right-hand rule, we're talking cross products, and kind of having an understanding of that vector 3D visualization skills, whether you want to rely on your visualization skills, or whether you want to kind of rely on unit vectors and kind of a notation which helps you account for all those directions properly. Everything in magnetism is really 3D because that's how cross products work. The two inputs take up a plane and the output is perpendicular to the plane in the third direction. So unless the answer is 0, there's something 3D about it. So here are some questions. Let me get a little bit bigger there.
You should be able to expand your window.
I'll just do that, yeah. Okay. So this one, clearly just kind of series parallel, not too bad. And maybe also questions about power, or just being aware of how to calculate power for an element, which is voltage times current. So if you could find those properties, you could find power, and the units are watts. What's the equivalent resistance between points A and B? And when this arrangement is placed in a circuit, a current of 0.15 amps flows in at A. Determine the current that flows through each resistor and the total power usage by the set of resistors. Mainly I would say there is, everyone will pretty much do part A fine and pretty quickly, and maybe make a small mistake, but I think people are pretty good at that. But mainly I would say is some people know how to do series and parallel, and then they get the equivalent resistance. They don't really know what to do with that or like how that is helpful for finding other pieces of information that are important about the circuit. But really, I would always think of finding equivalent resistance not as the end goal, but just a stepping stone to the real goals, which is figuring out current splits, figuring out voltage across different points and elements. That one's not too bad. I think there could be a question where it's not quite so obvious or easy to see parallel and series, but there you go. Somebody's saying something over here. Let's see that. Okay. Maybe this one. I think there will be a question, fair amount like this. Use Kirchhoff's laws to determine the current in each branch of the circuit below. Make sure it is clear which direction your currents run. So if you say left branch, 0.5 amps, do you mean 0.5 amps up the left branch or down? I don't have to guess at that, and so on. Did you have a question about the previous one?
Yeah.
Yeah. Going up here. Yeah.
So is
Sorry, I should have said
it easy to tell if the resistors are parallel? Because looking at the resistor with 10 and the resistors with 90, would that count? That wouldn't count as parallel, right?
If you do a calculation of 1/10 plus 1/90 reciprocal, that won't represent this circuit because those two resistors are not in parallel.
Okay.
Eventually, you can say something about 90 ohms being in parallel with the entire top combination.
That would work, yeah.
Yeah.
Okay. I was just double checking.
Yeah. So where would you start here? Where are there any two resistors you could start with right off the bat?
1/75 plus 1/150.
Yeah, those are in parallel, and I think if you do that, I think you'll get 50 ohms.
You take that, you add it to 10,
Yeah.
and then 1/that plus 1/90, and then add 30.
Yeah, it's something like that. And yes, that sounded correct to me. Let me just do this quickly.
It's just kind of
Can we just add more to our previous equation sheet? Wait, that was the long line positive or the short line? Batteries, long line is positive terminal of a battery. Short bar, short line, short bar is the notation for the negative terminal. I would say, can we just add more to our previous equation sheet? You won't need your previous equations for this test. They could come back around sometime in the future, but you definitely won't need Question about point charges and electric field and electric potential or force on this test. So I would probably just say you can just make up separate equation sheet, or would be my recommendation. What did I miss there? All right, cool. Okay, let's look at this one a little bit. We have 5 or so minutes. Let me just glance through the questions and come back to this one, I think. Use Kirchhoff's laws to determine the current in each branch. And you can see here, I guess, at one point in time, this was going to be a 20-point question, and the majority of the points were part A, but not quite all the points, not quite all the credit. Part B, which point, capital A, capital B, capital C, capital D, capital E, is at the highest potential and the lowest potential, and what's the potential difference between those 2 points? So basically, if you answered part A, you have a complete understanding of current in the circuit. And part B is saying, okay, well, let's spend a little bit of time and see if you can figure out some key information about potential or voltage. Now we haven't done the calculation here fully, but any thoughts about which point might be highest or one of the higher potential points, like any good candidates, the lowest potential points? I can tell you the answer for the final, I think it was like 1 point to fill this blank in, 1 point to fill this blank in, and 3 points to say what is the voltage between them. So I will tell you the answer for what is the potential difference between those points. The answer is not 3.5 volts or 5 volts or even 8.5 volts. Some other circuit with these guys, and it could be, but not this one. Any thought which point or points might be high voltage?
So when you're asking
Highest voltage.
lowest potential, it's voltage.
Potential is a synonym for voltage.
Okay.
In fact, potential is more like the key proper term, and voltage is just a nickname that's become associated with it because the unit we use to measure potential is called volts. And nobody uses any other unit. It's not like half the world uses volts and half the world uses, some other name after some other dude.
Yeah.
Everyone uses volts.
It's out there.
Yeah. People didn't start talking about this stuff till like 200 years ago, and it was kind of standardized pretty quickly. It's not like, well, France used meters, and England used feet, and other places used rods, and because people are measuring distances for a long time, but not voltages. So you can kind of think that through. What I would do to get started, I would label current I1 to flow either up or down this branch. You pick. Label current I2 to flow up or down the middle branch. You can pick. And I3 to flow up or down the right branch. You pick. And then my goal would be to write down 3 equations with those 3 current variables and all these given values. And then that would be a linear system of 3 equations and 3 unknowns. And by solving it, you will get the values, and with the values, the directions of the current flows. Okay. When you do Ohm's law, let's say you find the current. Let's go over here to the answers. So I'm looking around. Okay. Middle branch 0.25 amps down. Okay. So the middle branch, the answer is 0.25 amps down. So what's the voltage you get for this device right here? Let's just kind of jump ahead to part B a little bit. What's the voltage for the 20 ohm resistor? Well, I can do Ohm's law, right? If you've answered part A, you got the current. So 20 ohms times what current? Well, now we know it's 0.25 amps. So 20 times 0.25, that is a quarter of 20, which is 5 volts. And since the current is labeled here as down, which is in accordance with this arrow pointing downward, which end of this is the high voltage end? That's what the plus there and the minus there is saying. So it's not telling me the voltage at C is 5 volts. It's not telling me the voltage at D is 5 volts. It's saying the voltage step across that resistor is a change of 5 volts. So you really want to kind of have that idea clear in your head. Is this a voltage at a point? Probably not, but it could be depending on how you use the terminology. It's probably a voltage across an element or between 2 points. So, so what's the voltage from E to D, E to C? If we've decided that this is 5 volts with the high side at C and the low side at D, what's the voltage from E to C? Well, E to D, I go down 3.5 volts, and then D to C, I rise 5 volts. So E to C, if E and C had been the points that we need to find the voltage between, just take any path that starts on E and ends on C and add up the voltage steps along the way. And they better agree for path 1 from E to C and path 2 from E to C. Otherwise, your answers are inconsistent and don't actually solve the circuit. But apparently the voltage from E to C is higher in voltage than E by 1.5 volts. And both of them are higher than D. And if you keep going around and know all the currents, you can kind of fill in everything else. I think it ends up being D is the low voltage spot.
Yeah, it says
B and D.
high, D is
Yeah, the positive terminal of this battery ended up being the highest voltage of the circuit, and the negative terminal of this battery ended up being lowest voltage of the circuit. And you can work that out, or you can work out the details. Did I do no? Oh, yeah. So what about some magnetism questions? And just to kind of indicate what I mean about questions about both sources of magnetic field and effects of magnetic field, would you say that this question, if you were to read through it, is this about the source of the magnetic field B, or is this about an effect or effects of the magnetic field B? An unknown particle from a nuclear reaction, it's not going to affect our approach a whole lot, but we have some particle, enters a bubble chamber detector, that's this box, and follows the curved path shown below. The magnetic field is a known strength and it points in a known direction into the page indicated by X's in the diagram. And it's a uniform strength, same magnetic field throughout this entire region of interest. This field bends the particle's path and allows it to be identified. And the goal is to figure out which of these 8 particles is the red guy. The experimenters have determined that the particle is moving at a known speed of something times 10 to the 7 meters per second. And that the radius is, this is a section of a circle, and the radius is 34.2 centimeters, even though we're not seeing a completed circle or half a circle even. Identify the particle. So is this about the source of the magnetic field or the effects? It's about the effects. What does a magnetic field do to a moving charged particle? It bends it. And if it's a uniform magnetic field, it probably bends it into a circular arc, circular path. Could you guys, and you probably know very little about these 8 particles over here. Electron, maybe you know something about that, but we're given information about mass, charge, and charge to mass ratio. And then similarly for something called a positron with a symbol, muon and anti-muon, neutron and anti-neutron, proton and anti-proton. Can you guys tell me if this is a positively charged particle, a negatively charged particle, or a neutral particle?
It's not neutral.
It's not
That's
neutral.
charge.
It's not neutral. What would a neutral particle do? What would the neutron do if it were in this location?
It just looked
It
good.
would go straight. It wouldn't curve into a tight circle, a wide circle, a circle. Okay, it ain't neutral. Okay, obviously not. Basically, the idea is half of the stuff, the negative stuff's going to curve one way off of the straight line trajectory once it has to experience and move in response to the magnetic field. And the negative stuff's going to go the other way. At some point, you'd want to do a right-hand rule. And basically, you should be able to do right-hand rule. You could pick any point along this curve and do your right-hand rule. And you should come to the same conclusion. Probably the easiest point to pick would be when it just enters the magnetic field at the bottom edge. What's the right-hand rule? What's the equation that we're kind of dealing with here? I write it as a vector. Oh, it's right there. This one here, QV cross B. So if we pick right there, let's say we pick that moment, the velocity is upward, the magnetic field is inward, and because the curvature is to the right, we know there's a magnetic force here. I said FB, force due to B, FM, FB is to the right. And is that indicating a positive charge or a negative charge if I were to kind of highlight that location right there? Like this location right here. If you do right-hand rule, you'll get your thumb pointing to the left. And yet this object is actually curving to the right and it's actually experiencing force to the right. So what does that tell us? all the positive stuff would curve off to the left, and this guy's curving right. He's negatively charged. And then basically the more charge you have, the tighter of a curve you're going to be curved into. So now we need to know something about the size of the curve and maybe the speed, and we could say which of the negatively charged guys it is, and it turns out to be a muon. The radius is indicative of something with this kind of charge to mass ratio, which is either a muon or anti-muon, and the direction tells us it's negatively charged. And then, let me just kind of read this last question here. Or sorry, there's two more, but just this one, I think. Part A is about finding the source of the magnetic field question, and part B is like the effect. So a long straight wire is shown. A proton is a certain distance away, and it's misspelled the word wire, and it's traveling in a certain direction and speed. Part A, what's the magnetic field do to the wire? That's a B equals kind of question. Part B, what's the magnetic force exerted on the moving charge? And those are both vectors, they both have directions associated with them. And you could, I think in the solutions, it does this kind of once with kind of angles and right-hand rules and cosines and sines, and it does it another time with unit vectors. And then here's another source. In this case, the source is a current loop, and it's kind of perpendicular to the page, and you can try that one out. Well, that's not what I meant. Not a new share. I want to stop the old share. Okay. So kind of think that's what we're looking for. I would say if it's not in the chapter summary for chapter 30, 31, and 30, an equation is not in the chapter summary for 30, 31, and 32, probably isn't needed. The one equation that I might say that I don't think is written there that would be good is what is the magnetic field on the axis of a circular current loop? It's in chapter 32, but I don't think they wrote it explicitly in the chapter summary. Okay, I'll put the link up for the homework. I haven't made that live. Sorry about that. And you can submit your homework there, and I got a couple here in person, of course. All right, Hudley. All right, 34. Okay, comments. Signing off, everybody. Titus, Trevor, Conrad, Daniel.
Enjoy your weekend, Professor.
You too. See you Monday.